base. Our speaker here needs no introduction. Gilad has been the creator of the Newspeak programming language and a well-known researcher in the area of object-oriented programming languages. Today, he's going to give a talk on Array of Hope, array programming for the 21st century. The talk will be 40 minutes, followed by a 40-minute question and answer session, which could turn into an Ask Me Anything session. I'll be moderating and looking at the question answers on Clouder, YouTube, or the Zoom chat, or you could also raise your hands and ask questions. With that, I hand it over to Gilad.
Okay, so I'll share my screen. I hope that works. This doesn't look good. Let's try this. Okay, open system preferences, great. Hang on, we have okay, Zoom will not be able to record. Let's see if this matters. Let's try and share again. Yes, this looks better. So can you actually see the, this may not be the right thing. We probably want to share this actually. And then we want to,
Yep.
That working?
Yes.
Okay. All right. So thank you everyone for coming, and good afternoon or evening or morning or whatever it is, wherever you are. The organizers build this rather optimistically as the future of array programming. I have no such pretensions, but I hope it is a future, a possible future that is of interest. And so before we talk about the future, I'm going to briefly talk about the past, because I think being aware of the history of things is very important so that you can make your own mistakes rather than repeat them. And so briefly, for the benefit of perhaps some of you who are not very familiar with array programming, and certainly for some, hopefully, people who watch the recordings later and so forth. In 1962, Ken Iverson published this book, A Programming Language, which described a paper and pencil notation, a mathematical notation that wasn't actually implemented on any computer at the time, even though he'd been working on this since something like the mid-50s. And it wasn't implemented for a few years till the mid-60s. So 10 years between concept and implementation. Try doing that today. We'll see how much rope people will give you. But the results were worth it, because it basically was something totally original. And we're talking 1962 here. So we're 58 years. It's 2 generations ahead of its time, because I think its time is now. And it has had an influence, even if people tend to forget, a pretty important influence on both functional and scientific programming. So array programming in a nutshell, if I can get my slides to change. Interesting. Hang on a minute. Beautiful. Let's see if that works. Okay, that works. Okay. So basically, the idea is that everything is an array, specifically a multi-dimensional array, which means these are rectangular arrays. It's basically everything's a hyperrectangle, or an orthotope is another word I found for these things. But somehow everything is an orthotope, doesn't have that nice marketing ring to it. And the important thing is that all operations are lifted to these arrays. And that's really what makes this interesting. And they're lifted in a pretty particular way, which we'll get to. And that can be very, very powerful and very useful. So as the simplest example you can think of, perhaps that's even ever so slightly realistic, is a dot product, right? We have A and B as n vectors of numbers. and we're going to multiply them pointwise, every element of A with the corresponding element of B, and sum the results. So of course we could do this the traditional way, which means we'd have to initialize an accumulator to 0, and then loop through with indices from 1 to n, and use them to index into each of the arrays, multiply them out, add them to the accumulator, assign the accumulator, and keep going, right? Or you could write something like this: reduce plus on A times B. So when you see reduce, you might think of functional programming. For what it's worth, this is where they got it from APL. The reduce as a programming construct was introduced in APL, and there's a reason it's named reduce, which we might mention as we go along. But it isn't, there's more going on here than the reduce of functional programming, because if we were to write something in functional programming, it would look something like this, right? Because there's this whole process of mapping that basically does the pointwise multiplication between these vectors that has to happen, and functional programming will not do that for you. Depending on the exact formulation, you might, for example, have to zip these two together, so you get an array of pairs, and that you could feed into your binary times function with map, and then you could do a reduction on that. Or you might have currying and do 2 maps instead, or you might have zip2 or map2, or there's all kinds of ways you can formulate it, but you're going to have to do something, because the intuitive notion of just multiply these 2 pointwise is something that the language doesn't do for you. And that's one of the things, part of the process that array programming does do for you. So what's good about this, of course, there's a concise, clear notation. It's close to the underlying math. And most importantly, I think, is that iteration is implicit. It's based on the shape of the data. So you don't have to deal with the mechanics of iteration. And as a result, you don't get indexing errors, and you don't get infinite loops. In fact, what's interesting is you can actually make these programs completely useful and do pretty much most things you want to do without making them Turing complete. They don't actually need to even support, they certainly don't need loops, but they don't need to support recursion either, because the shape of the data tells you how to iterate, and you can do an amazing amount of stuff with non-Turing complete language, which is interesting. And the other important thing is it's easily parallelizable, because unlike work that many clever and good people have done to take, say, a traditional compiler and have it figure out that this mess can actually be done, the multiplications can be done in parallel and the addition can be done in logarithmic time, you can just take a construct where it's known that it does that. So rather than have the human encode this mess and then have some other human struggle mightily to produce a compiler that can decode such messes, you can spare all the humans and the compilers a lot of time and trouble, and simply express it in a way that is obviously naturally parallel. The other thing that I really like about this is it makes you think different, because it encourages a mindset that's inherently parallel and very different from what you get with traditional programming. So this is an example that I've shown in various cases in the past, but now I've got it, rather than in APL and explaining the strange markings that constitute APL syntax, I've got it in ShapeRank, and it's a bit more readable, I hope. So we're going to compute all the prime numbers up to some number n. And to make this concrete, we'll set n to 6. And then what happens here is, first of all, we compute this vector r. So r is 2 to n, because this is a fairly intuitive notation. It's basically sugar for a call to the range function that takes two numbers, a start and an end, and produces a vector from one to the other. So we get 2, 3, 4, 5, 6. And with this vector, we're going to compute the outer product. Outer product in math, applies to tensors and does all products of all the possible combinations. We're not mathematicians, and we can't just say that product is whatever we mean it to be under certain rules. And instead, we specify what function we're going to use, and in fact, it doesn't really have to obey any real mathematical constraints. But in this case, we'll just do times, and it'll time the 2 arguments here are the same vector r. And so we're basically getting a multiplication table, right? 2 times 2, 2 times 3, 2 times 4, etc., down to, 6 times 2, 6 times 3, and so forth. Now, with that, we're going to see whether it can, we're going to call contains, and contains is a function that takes some array of any size or rank or whatever, and checks if a given element is in it. Now, the funny thing is that we're passing it a vector, not an element. And so we're going to apply this pointwise and check for each element of R, for each of 2, 3, 4, 5, 6, whether it's in this outer product. So we can see that 2, for example, which is the first element, isn't in the outer product. We can see it, it's not in here. Same for 3, it's not here, but 4 is here, and so we get a true. 5 is not, but 6 is. And so this is the Boolean vector of the results of for each element, whether it's there or not in the multiplication table. Now we can negate that. That again is easy. That's pointwise. So we're getting true, true, false, true, false. And then we apply mask, which is basically a filtering function. We're basically applying it to R. So we're going to use this Boolean vector as a mask on the vector R. And what that means is if the Boolean vector is true, the corresponding element in R will appear in the result. And if it's false, it won't. And this will yield 2, 3, 5, which coincidentally are the prime numbers below 6. And so it's kind of, when you look at it, you said, well, what would we do here? We computed all the products of all the numbers, from under 6. And then we check to see if a number is there or not. If it is there, it's a product and therefore not prime. And if it isn't there, since we have all the products, it can't possibly be a product, and it is a prime number. And so when I first saw this, it sort of blew me away because this is such a unusual way of looking at this problem compared to what you're typically taught with sequential algorithms. And even though you might say this is a crazy algorithm, right? It's n cubed and so forth. It's a different way of looking at things. And there might be a circumstance where this might make sense, right? You want an answer in a hurry. You have lots of processors. You've got 16,000 cores on some big GPU chip. And, you don't care how much work it's doing in terms of operations. They're n cubed, sure, but you really care how fast it can do them. And this way it does a lot of stuff in parallel. And I'm sure it's probably not the best algorithm ever, but it illustrates the weirdness and wonderfulness of the array programming languages. So, of course, I'm not the first person to be enthused about these. And Alan Perlis, of course, endless source of wonderful quotes about programming languages, had a quote about this one. And you might ask, well, since he says it's an almost perfect instrument, what gave me the idea that, to go tamper with it? Why mess with it? And of course, APL was not quite perfect. Certainly when it was created, it did have, even though it was visionary and generations ahead, there were artifacts of its time. It had go-tos and, there's some strange stuff, but those have been cleared out by later dialects of APL or successor array programming languages. There's a slew of them, A, J, K, Q. They're very fond of one-letter names. And most of these have done away with the strange notation, and even though there are people who really like it, and modernized it. And so really the question is, why are we tampering this? Why can we do it? Why do we think we can improve upon it? Well, first of all, as Perlis says, we can improve upon it in small ways, because yes, the fundamentals are there. So you build on something really, really powerful, and maybe you can tweak it. If you're careful, you don't ruin it. So the first thing that we're trying to do is to move from arrays to streams. Streaming is obviously very useful and hot right now, and we're basically extending rank polymorphism to streams. So rank polymorphism, for those who might not be familiar with the term, is a fancy way of describing this process of lifting all the operations to arrays. It basically means that you can write code that is polymorphic over the rank of the array, that is the number of dimensions. Unlike no matter how much traditional programming you use, functional operators like map and so forth. You know, if you get a list, you have to map over it. If you get a list of lists, you have to map twice, or you're aware of the structure. Whereas the beauty of array programming is that you can write code that works for arrays of any rank, and that's why it's rank polymorphism. So extending that to streams is something that I'm working on. It doesn't work yet, which means it could also be wrong, but I'm going to tell you how I plan to do it. It seems like it will work out. And when the implementation is complete, I'll know that it either did work out or that there's some tweaks that have to be done. But I'm pretty confident that something like this is going to work nicely. And once we have that, we're also going to try and incorporate various constructs for query support in the style of, say, streaming SQL, with where you have to define windows on streams, and that takes you back to finite arrays of finite size, and so you need the array programming part there as well. The reason I think that I personally am kind of really keen on the stream thing is reactivity. So obviously reactive programming has been, you know, a hot topic, and it's had a huge impact on UIs and so forth, but the concept is more general than that. And I tend to think about things that are near and dear to my heart. So for example, incremental programming environments where you want to make changes and have them be processed instantly and quickly, and therefore you want to do it incrementally. Reactivity helps a lot with that, because once you have rank polymorphism over streams, essentially all your programs are implicitly reactive, and if you do it right. And from reactivity to incrementality, there's a bit more, but you've gone a large part of the way, and everything is a lot easier to express. So the other thing that we're doing, you know, in terms of small ways to improve on an almost perfect artifact, is static typing. And this largely is stuff that I've stolen from other people. So there's great work at Northeastern, Justin Slepat's PhD thesis, which I'm not quite sure, but should be done real soon now, I think. He's done all the heavy lifting for figuring out a lot of the issues with typing APL. Now there's been other work, there's earlier work which have type-checked more limited subsets like SCA. And there are several reasons this is, I think, is important. One is that obviously sometimes being able to type check the dimensions, that's the key thing, right? It's not really that we're interested in type checking whether it's an int or a float. That's as good as it is, but it's hard for me to get excited about that. It's really about type checking the dimensions of these arrays and making sure that you're composing them in ways that make sense. And I got interested in this when I worked a little bit with TensorFlow a few years ago. And I found that it had managed to combine in, the worst of all possible worlds in certain respects. And I think it's gotten a bit better since. But basically the problem was, you wrote this program in Python, and obviously there was no static typing, and your dimensions of your tensors did not match. And there was no type system to tell you that. And usually in Python, that's not a big deal, because you can look at the tensors yourself. You can actually look at these data structures and see and figure out what their size is. But with TensorFlow, you weren't really working with them. You were writing a program that was going to define a data flow graph that would work with them. And so you didn't have real data in hand. And so you had neither static typing nor dynamic typing. You were basically flying blind. So it would really be nice to be able to type check these things. But more important than that are issues of performance. So, whoops. Basically, if you're, again, being able to know what the dimensions of things makes it easier to compile it and figure out what the loops that you're implicitly generating and so forth are going to be like. But as long as we were on CPUs, this wasn't such an important thing, because if this optimization really mattered, it mattered because you were dealing with large bodies of data, large arrays. If you have large arrays, the cost of dynamically checking this stuff and figuring it out on the fly in your kit was amortized over all this data. In fact, APL, as far as I know, was the first language to have JITs. That's another contribution that they've made. Now, this is different now in the world of GPUs and TPUs and all these special purpose processors because they're much more rigid and less flexible. While they will do wonders in terms of performance, it's really hard to do this kind of dynamic stuff on them, and it would be really nice to know it in advance. And even more so, say, if you're trying to compile to an FPGA or something. So there's the classic reason performance for types is very important. So we're doing basically some variation on what the Remora language that Justin Slepak developed is doing, but we're doing some things a bit differently, and we'll get to that. So, quick overview of ShapeRank. It's a functional, statically typed language, and like APL, all the higher order functions are built in. We're at this point not allowing user-defined higher order functions. We should be able to extend it to that, but we're keeping things as minimalist as we can. By the same token, obviously there are no loops, but there's also no recursion. It's just going to be based on the input data and the shape of that data. All the values are tensors, or if you want to call them something else. I'm acutely aware that I'm abusing the term tensor because on computers, they aren't really tensors. Even if you're just doing floating point numbers aren't a field. And certainly other things we put in these tensors like records are not a field. But it's a short and concise and a word. And as I said, orthotope doesn't quite sound right. An array is very muddled. Array is used for like Java arrays where they're jagged. So rather than use arrays for now, I'm using tensors. That may change. And of course, all the types are tensor types, which we'll get to. So key concepts, obviously you all know what scalars are. The only one thing that's a little weird is that we're considering records as scalars, because for the purposes of these languages, scalars are the basic units that go inside the arrays of any rank. And records with named labels, they're not arrays, they're just basic data types that are sort of the smallest granularity elements of these arrays. So for our purposes, they're scalars. Tensors are the multi-dimensional arrays, like 1, 2, 3, or matrix, for example. We write them in a fairly obvious manner. So it's written as an array with individual vectors in it, but really should think of its structure as being essentially flat. Now, every tensor has a shape and a rank. The shape is a vector of numbers that describe the sizes of all the dimensions. So if it's a vector like 1, 2, 3, the shape is 3. If it's a matrix, then the shape is 2, 3, and so forth for any number of dimensions. And the rank is actually that thing, the number of dimensions. So vectors are rank 1, matrices are rank 2, three-dimensional things are rank 3, etc. And it's always the case that the length of the shape is equal to the rank. And of course, very importantly, scalars are tensors too, because we need this to compose and to be very uniform. And so we take the view that scalars are tensors of rank 0. So their shape is an empty vector. There's 0-dimensional vectors, if you will. So then we can look at what this lifting implies without getting fully in the time we have. It's kind of hard to get into the precise algorithm, but you can read about it in the Remora papers. And if we have time in the questions, we can get into that. But basically, you have a vector or any rank, it could be a matrix or anything else, and you apply a unary operator like unary minus. Well, you expect it to operate pointwise, and that basically means that you're applying map implicitly. This works for any number of arguments, unlike APL where it was restricted to 2. Basically, you have these two vectors, and you're going to add them pointwise in the obvious way. And as I said, one way to look at this is the idea that you're zipping the two vectors into a vector of pairs, and then you can map a binary operation that takes pairs and produce the result. So we're doing a zip and a map implicitly. Then when you do something like this, like again, the common notation 2 times A, that's really equivalent to a vector of 2 is 2, 2, 2 times A in this case. And so essentially there's an implicit replication going on basically we're replicating the scalar 2 to make it to the shape of the target, in this case a 3 vector. And then when we have that replicated vector, we can zip it and then map it. So all these phases are happening. They're basically part of the semantics of function call. And as I said, it works for all ranks. So if you do this, you can multiply a matrix by 2, and then you'll get 2, 4, 6, 8, 10, 12, etc. And then you can add a vector to the matrix, and the vector will get replicated such that we add the vector to each of the rows of the multiplied matrix to give us this result. So all of this is kind of part of the standard APL magic, and there's nothing really new there. Now, as far when we start doing streams, we do have to think about what the model is. So streams are basically vectors of unbounded length, of an unknown length. It might be finite. It's in reality, it's always finite, but it certainly is not something that we know in the program what it will be. And then we basically generalize the multidimensional arrays to be multidimensional streams, and still apply the rules of rank polymorphism, as we'll see. So the regular ones, the regular tensors, are just a special case where we happen to know what the length is going to be. So let's look at our examples again. If we have a unary operator and we have a stream, well, you can do map on streams. So if you have someone supplying you the integers, say from a Haskell program, which is good at manufacturing streams, then you just produce a stream of the negative integers as a result. If you're adding two streams, things get a little more interesting because you have to do the zip. And in this case, we're going to, at least for now, we're going to zip the elements pointwise. So we'll get the same things and produce a stream of pairs zipped, and then do the mapping on it and get the stream of results. But there's interesting things going on here, as we'll see in a moment. Now the replication, also, we multiply a stream by 2, we have to basically turn it into a stream of 2s that goes on forever. Basically, if we do replicate with question mark representing the shape of a stream, the unknown kind of dimension, then it's going to produce for us a stream that, whenever you ask it for another value, it'll give you the same scalar back. And so we can then actually zip it and produce and map and so forth. Now, the thing about zip is that the way we presented the example with zip, it was doing something interesting. It was implicitly synchronizing these two streams, A and B, because it would produce a new value when both of those streams have a new element. And if one of the elements wasn't, if the streams are produced at differential rates, as they typically are in reality, then we don't have data to zip, and we'll just wait till we do. Now that's not the only interpretation we could have of this zipping operation. We can think of a reactive version of zip that produces a new value when either stream has a new element. So if we look here, let's say that we have these two streams again, tens and hundreds, but hundreds are slower. So we only have 2 elements so far of hundreds, and we have 3 elements of tens. And in the previous version, we would basically we would pair 110 and 220 and produce the first 2 values. And then we'd be waiting till 300 showed up, and then we could add a new element. So it'd be synchronizing. However, in a reactive program, that's not what you want. You really want the function to produce new results whenever any input has changed. And so rather than using this as a synchronizing operation, we'd like to basically find a way to produce new values. And an easy way to do that is say that if we have a new value on one of the streams, we'll pick the latest value. If there isn't one, we'll pick the latest value that we have and use that. And so that corresponds to what will happen in a program where one of, you want it to be reactive, one of the inputs is changing, the others may not be changing, and you just want to compute what the change to the value of the function is, given that one of its inputs has changed. Now the problem is, if this is folded into the semantics of the language, how do we decide which streaming operator to use? And so my inclination, at least the design so far, which isn't running yet, is to allow the functions to choose that. And the default, I think the more useful default, is actually the reactive semantics, which means that if some stream argument has a new value, we trigger the computation, basically. And in terms of the zip, that means it's the reactive zip I just showed you. If, on the other hand, we should be able to, because I'm sure it's useful in other cases, to have the synchronous semantics. So if you specify it, you can make sure that you only produce a new value if all the streams have given you a new value. So that's kind of the plan for streams, or at least the highlights of it. As far as types, I wanted to show you a bit on the types. So the types consist of two things: the shape and the base type. The base type is sort of the types you know and love or hate, as the case may be. And this is one of the things we're doing different from Remoron. As far as I know, the Remoron work intends to basically do global type inference. So you never have to write these types down. And that makes sense, because these types, like sophisticated type systems, everywhere they can get pretty gnarly. However, global type inference, I've never been a fan. It tends to create situations which are hard for people to, when things go wrong, when there's an error, it's hard for people to localize the error, because there's an inconsistency somewhere in the entire program, and it usually, the compiler has a hard time pointing you at a specific point, which is really what you would think the source of the error is. And so I'm much more fond of things like local type inference. And that's what we're doing. And again, this idea isn't new. It turns out that SCA has been doing that. SCA is a array programming language that is typed, but is limited in the kind of constructs that it can type check. But they do the something similar. And the downside of that is that you do have to specify the types in function signatures, and that's a mixed bag, because on the one hand, it's actually nice to have them, and it can add readability, but it can also inhibit it, because sometimes these types are not simple. But that's what we're doing. And so our main type innovation is probably the fact that, yeah, there's a pretty fancy local type inference algorithm, and that is mostly working. So let's take a look at what these things look like. Again, for some literals. So the stuff in blue here is the type. So this is a vector, a 3 vector, and this is its type. So 3 here is actually acting as a type. It's dependent types, right? Types as values, or values as types, or whatever you want to call it. And of course, in a very restricted form that doesn't go off the rails and is decidable and so forth. But basically, this is the actual type of this vector. So we actually compute array sizes and things like that. If it's a matrix, then we write the shape element by element here, 2, 3, and then the base type int. Now, let's see, right, some examples of functions signatures. And so, you can write plus just the way you would in a conventional language. So there's a shape, but we're not writing it. The idea is that the empty shape can be elided, which makes things a little less noisy. If you do want things to be a vector, then you do have to put a shape, but you don't necessarily have to put in the dimension, because we'll basically assume that if you don't write a specific dimension, it's some variable that, size that we have to infer. But you can write them, because sometimes it matters, and they're used to express dependencies. So if you look at append, it takes 2 parameters, obviously, and they have some base type t, which we don't care. It's a type variable, and so this will probably change syntactically. But right now, it's a quick hack to let us recognize what's a type variable and what isn't with the ugly dollar signs. So this implicitly declares a type variable t for the element type, and we don't really care. It just passed through, right? It's unbounded, you know, parametric polymorphism. But what's interesting is what's going on here with these dimension variables, as I call them. Essentially, we're saying that the first argument has some length, you know, it's a vector, there's one dimension, and it has some length d1, the other one is some length d2, and append will actually produce something of length d1 plus d2. Now, contains, we saw contains before in our example with the prime numbers, so it doesn't care about the exact dimensions of the first argument. It is of some shape, and this is the thing with the at sign, at s is a shape variable. It says it is some unknown shape s. It'll work for any shape, and it doesn't really care. It takes an element of the same type as is contained in the array that is its first argument, and it returns a Boolean. And again, we're not giving the dimension here because it's a scalar type. So this is kind of what things look like. They can get a lot fancier. As I say, I've tried to keep it simple because in the time I have, I can't really cover this in a lot of detail. Sometimes we need a dynamic typing. If you look at the example in its full glory with the mask, the problem is that at this point we don't know what the size is because we're masking it. It depends on the dynamic contents of the data, not only on the shape of the data, but on their contents to determine the shape of the results. So dynamic dimensions are useful as well. As I said, streams, the dimension of streams is denoted by question mark. And yeah, there's a few more details, but we're kind of running, I think, short on time. So where are we with this? There's a prototype reference implementation. The goal of that is to actually validate these ideas. And at some point, I'll find a friendly theoretician who can actually prove that this stuff is correct as well. But I'll be happy when the implementation works on all the examples and all the things I can think of. And there's still some bugs. The stream support is missing, so that's a big unknown. And yeah, I'm working on a specification, and eventually there will be a paper because I think the inference algorithm is probably interesting enough to write a paper about. And we'll be open sourcing this in a repo that you can't access yet because it has to be set up to various corporate standards. And when I started doing this, I realized there was a lot more work than I thought, so I'm behind. And people who want to, you know, more of the history of the topic. I gave this talk about the history of programming languages last year, and it's on my YouTube channel, and it kind of discusses a lot of the APL story in a bit more detail. So that is the essence of the talk. And at this point, I guess we can go over to the questions, if I can figure out how I can see you guys again.
Thank you, Gilad. Let's thank the speaker. So, we have